Hello, everyone. My name's Scott Clark. I'm co-founder and CEO of SIGOPT, a company that specializes in providing Bayesian global optimization as a service. Very excited to be talking to you guys today about what that means, why you should care, and kind of dig under the hood and show you a little bit of the math behind how these methods actually work and how they can be so powerful. So throughout the talk, if anyone has any questions, feel free to drop them into chat. I'll try to address them here. If not, I can provide references after the talk as well. Some of this gets relatively deep, but there's a lot of great literature, textbooks, blog posts, etc., out there that I can point people to. So for this talk, I'm going to tell you why tuning machine learning models are hard, why you should care about this problem, talk about common ways that people do it today, talk about Bayesian global optimization, once again diving a little bit deep here to explain intuitively why this is a better method than what people typically do today when it comes to tuning large AI pipelines. Walk through a couple deep learning examples. All of these are available online with code as well if you want to try them at home. And then if there's time, I'll talk about how you would go about evaluating different optimization methods in an extremely robust way, diving into one of our ICML papers from last year. So first, I'm going to tell you two things that you already know. The first is deep learning and AI is extremely powerful. You wouldn't be watching these presentations today if you didn't already believe this. It goes without saying that more and more things are being transformed by these methods, from banking and fraud detection in banking, recommendation systems, algorithmic trading, as well as just entire verticals that were maybe not as data-driven historically, like oil and gas or retail, are becoming more and more powered by AI and deep learning techniques. The problem is tuning these systems and getting them to their peak performance is extremely non-intuitive. And what this means is oftentimes a lot of domain expertise goes into building that data pipeline, understanding the data, understanding your customers, understanding the context. But at the end of the day, you need to be able to get it to its peak performance before you put it into production. In fact, in a recent interview on Quora, Xavier Amatrian, who's formerly the VP of Engineering at Quora and Director of Research at Netflix, said that this was one of the most important unresolved problems in machine learning. So he talks about how it's kind of difficult to understand what's going on underneath the hood in these deep learning systems and how explainable they are, but also having a more or less automatic way to determine their architectures and hyperparameters. So that's what I'm going to go in today and make the case for why Bayesian optimization is a pretty good way to attack this problem. So I'll start with an analogy here, or I'll start to try to motivate this a little bit. Every single machine learning and AI problem has these tunable parameters. From the simplest random forest, where you need to select the number of trees, to the most complex neural network, where you have architecture parameters, learning rates, stochastic gradient descent parameters, etc. So this is a relatively simple neural network. It might be familiar to some of you. This is playground.tensorflow.org. It's a really fun website where you can tune a neural network in your browser. So what it's trying to do here is 2D binary classification. So what we're trying to find is a surface that is orange where there's an orange dot and blue where there's a blue dot. So you can imagine you're working in a bank and you're doing fraud detection, and you have this binary classification problem where the orange dots are fraudulent transactions, the blue dots are good transactions, and you need to be able to predict whether or not a specific transaction is going to be fraudulent. So once again, as a data scientist or as that domain expert, you can understand the data, your customers, that business problem that you're trying to solve. But before you even start training this underlying network, you need to select the configuration parameters, the hyperparameters, things like learning rates, number of hidden layers, number of neurons per layer, transformations of the data, etc. And this is completely orthogonal to that domain expertise that led you to build that specific model or to provide that value to your customers. And so oftentimes it's just attacked via trial and error. But worse than this, it's often not done via some pretty graphical interface either. What happens is in these popular open source libraries like MXnet here, there just exist many different magic numbers that live throughout the entire system. So this is the RMS prop stochastic gradient descent optimizer within MXnet, and this is the documentation for it. So you can see we're implicitly defining a learning rate, gamma 1 and gamma 2 and epsilon parameters, and these are going to affect how well the weights converge, if they converge at all within that neural network. And the problem is, as you dig a little bit deeper into the documentation, and this is the full extent of it, you don't really get that much intuition about it. So gamma 2 is a momentum factor, and it's only used if centered equals true. That doesn't really give us that much information about, well, should it be higher for more data, lower for more data? If I'm not converging, like how do I change all of these different things? How do all of these parameters interact to affect the overall accuracy of that fraud detection model? And this can feel a lot like trying to climb a mountain in the fog, where let's say you needed to get to the highest possible altitude on this mountain, and I let you tune your latitude and longitude. So it's very time consuming and expensive for you to hike up to that very specific place that you define and measure your altitude. And it's a foggy mountain, so you can't necessarily see even which way is up. And it's this very time consuming and expensive trial and error process. And tuning these machine learning and deep learning systems can feel the same way. It's extremely time consuming and expensive to spin up a bunch of GPUs and train a big TensorFlow network. And so you need to be able to get there as efficiently as possible. So there's a few standard ways that people attack this problem today. As I said before with SIGOPT, we talk to a lot of different firms around the world trying to attack this problem. And so typically what we see, probably 90% of the time, is a model's already in place. They're doing fraud detection, have a recommendation system, an algorithmic trading strategy, whatever it may be. And they have some model and some way to validate the output of that model. So this is kind of what you need before it becomes an optimization problem. But then at this point, there's all these parameters that go into that model, and they affect that output that you care about. So 90% of the time, people are attacking this one of three different ways. And these are also kind of the most commonly advocated ways to attack the problem in the open source itself. So one option is doing an exhaustive grid search or brute force approach. The idea here is laying down a grid of a bunch of different possibilities and trying them all. So back to the mountain analogy, this would be trying every single lat-long pairing and exhaustively searching over the entire landscape, and then at the very end seeing which one got you the best. So the nice thing about this is that it's relatively intuitive. Depending on how coarse that grid is, you're kind of guaranteed to get at least within some distance of the actual best result. But the problem is it's incredibly expensive. So it scales exponentially as you get more and more parameters. So tuning something like a random forest this way, where maybe you're only tuning the number of trees and the number of samples needed to split a node or something like that, maybe it's fine because it's relatively cheap to evaluate and you're only doing a grid of dimension 2. But as you start to look at gradient boosted decision trees or neural networks, you start to look at 5, 10, 15 dimensional hyperparameter spaces, all of a sudden that exponential penalty makes this completely intractable, which is why some people have turned to random search. There was a famous paper in 2012 by James Bergstra showing that random search in expectation should be able to get to better results faster than grid search. So it's just like a more efficient way on average to get to the same or better results. And this has become very popular in a lot of different online libraries as well. The problem with this is it's a very uninformed search. This is like trying to climb that mountain by jumping out of an airplane and hoping you land at the peak, and then doing that over and over and over again until you're satisfied with whatever the highest altitude you were able to measure. And as these systems get more complex and as these surfaces that we're trying to optimize get more and more pathological, this strategy can break down pretty quickly and can be incredibly inefficient, especially if every single time you want to try a new configuration, you once again have to spin up a cluster and incur all of this expense, both in computational time, but also potentially wall clock time, delaying the release of that product that you're building. So another way that's very popular, and some people feel very comfortable with, is manual search. So the idea here is, don't do the exhaustive search, don't do the random search, just try to do it in your head. Once again, when you're tuning a simple problem, simple pipeline, this can actually be relatively efficient. If you're only tuning the regularization parameters of logistic regression, you can kind of understand the trade-offs you're making as you tune this. The problem, once again, though, is as this extends to higher and higher dimensions, humans start to be very bad at doing optimization. So it's very difficult to do 15-dimensional optimization in your head. And when humans try to do this, at best, they find very localized solutions. And so they're very unlikely to find a novel solution far away in that configuration space that actually outperforms what they've been able to kind of locally tune and tweak towards. Other popular methods for this are genetic algorithms, simulated annealing, particle swarm-based methods, randomly restarted convex search. The problem with these are sometimes they're difficult to set up, but they also make the assumption that it's relatively cheap to evaluate the underlying infrastructure or the underlying configuration that you're testing. And so they tend to be orders of magnitude slower than the Bayesian methods that I'll introduce here in a second. So the intuition for how these methods work is that we create this optimization feedback loop. So once again, we're going to take the exact same model, exact same pipeline that might have been tuned via grid search, random search, or manual search before. We're going to have some optimizer suggest configurations to try. We're going to observe the output of those configurations. So imagine we're tuning the number of hidden layers in a neural network, and then we observe the accuracy of this classification method. We then learn from that to decide what to do next. So the idea here is we can leverage this very time-consuming and expensive to gather information and use that to decide this is the most intelligent thing to try next. And we repeat this process, and that will guide us into better and better parameter configurations. So the intuition, again, here is trading off exploration, which is learning more by trying different configurations and learning more about how that underlying system responds to those configurations, how the parameters interact with each other, over what length scales, how they combine together to influence that output we care about. So that's exploration. And we trade that off with exploitation, which is once we have some information, how do we use that to drive you to higher and higher results? How do we resolve kind of localized good configurations? And the goal here is to do this in what's called black box optimization. So we're not introspecting the underlying model or calculating things like gradients or kind of requiring any domain expertise about what's actually being tuned. All that happens is inputs come in and an output comes out. And we're trying to maximize that output in as few attempts as possible. So I'll go into some detail about how that actually works underneath the hood, but I'll pause here. I noticed nobody's had any questions in chat. Once again, if there's any confusion about any of this, please just pop them in there and I'll answer them as I go. So Bayesian global optimization. Intuitively, this might sound like a better way to solve this problem than brute force grid search, but how does it actually work? So first, I'll define it. This is my academic family tree defining optimal learning, which is what these methods are called in operations research. So we have my PhD advisor and his PhD advisor. The idea here is, how do we collect information as efficiently as possible when sampling the underlying system is time-consuming and expensive? Okay, we got one question. I'll address that here in a second. Or how do we just kind of get to the most money as quickly as possible? So the idea here is to optimize some objective function, like loss, accuracy, likelihood, given some parameters, like hyperparameters, feature parameters, architecture parameters, and we want to sample that underlying system as intelligently and as few times as possible. So we have extremely sparse amounts of information. So to address the question in the chat, this differs from some other methods in the sense that there's lots of ways to do optimization. There's lots of ways to attack problems like this, but our goal is to do it in the most kind of sparse way possible. So we only have maybe dozens of specific configurations that we want to try over the course of this entire system. And we have no underlying knowledge of what's going on underneath the hood. And so we're not necessarily trying to build a model for the underlying system that we're optimizing that we'll use in the future. We may build models along the way to decide what to do next, but the goal is basically just to, in this kind of meta optimization sense, attack the underlying system and optimize it in as few steps as possible. So how does this actually work? In the computer science literature, this is often referred to as sequential model-based optimization. Once again, in operations research, it's called optimal learning. A lot of fields have built this up in a variety of different ways. Some of the original research behind the form of Bayesian optimization I'll show today date back to the 50s, the Kriging-based methods for trying to figure out how to efficiently place gold mines. So lots of fields have invented this in a lot of different ways. But yeah, the goal here is to, as someone in the chat just mentioned, to reach a good result as quickly as possible. So sequential model-based optimization, I'll break this down into different chunks and then dive into them in quite a bit more detail here in a second. But the sequential nature is we're going to learn from the history to decide what to do next. So once again, this is how it differs from something like a grid search or a random search, in the sense that we're going to leverage what we already know to decide what's the most intelligent thing to sample. It's model-based in the sense that we're going to build up different surrogate models to decide how we're going to efficiently sample the underlying system. So the intuition here is, instead of doing something like a genetic algorithm or simulated annealing or something like that directly on the time-consuming and expensive to sample pipeline, what we're going to do is we're going to leverage what we've already observed to build up different surrogate models for how we think all these different parameters interact, and then we can throw the kitchen sink of optimization at that in this cheap to evaluate space to decide what to do in the expensive space. So that's the optimization component of this. Once we have a surrogate model, we want to decide what's the most intelligent thing to sample. We sample it, and then that updates the whole process. So once again, this is sequential in nature in the sense that it's learning from the history and constantly updating that to decide what to do next. This can, of course, also be done in parallel, but information needs to go through this optimization loop to leverage what we've already historically observed. So I'm going to walk through a specific path through the Bayesian optimization literature here using sequential model-based optimization. This is probably the most popular approach to Bayesian optimization, and there's a lot of different open source libraries out there that use this specific approach, including the metric optimization engine, which I wrote while I was at Yelp. BayesOpt uses this, which another SIGOPT research engineer wrote from the University of Zaragoza. Spearmint uses this approach. GPyOpt uses this approach. So this is kind of the bread and butter go-to Bayesian optimization strategy. The idea is we're going to use a Gaussian process for the surrogate model. We're going to fit that Gaussian process as efficiently as possible. We're going to find the highest expected improvement on that, that surrogate model that we've built to decide what to sample next. We'll sample it and then update this whole process. So once again, we'll update the posterior of this Gaussian process to get a better idea of what's happening underneath the hood, and repeat this. So I'm going to dive into more detail on each one of these in a second. There are also great books and articles out there. This method itself became popular from a paper from 1998 called Efficient Global Optimization. There's also a great free book on Gaussian processes called Gaussian Processes in Machine Learning from MIT Press, available online for free. Highly recommend those. So, yeah, I see not really a question in the chat, but an answer to a previous question. Yeah, once again, what this is designed to do is tune kind of these meta parameters, these hyperparameters of the model. This is not a replacement for stochastic gradient descent within a neural network. It's designed to maybe tune the parameters of that itself in this extremely sparse setting. So first up, what is a Gaussian process? All right, there's two ways to think about this. Once again, a lot of great books and literature out there on this as well if you want to dive into the math. The way we're going to use this as basically a way to do stochastic regression. We basically want a surrogate model for how we expect this underlying pipeline to react when we feed in different configurations. So let's say there's only one parameter we're going to tune. We're going to tune the learning rate of some convolutional neural network. And there's some objective that we're shooting for. This could be, once again, something like accuracy, could be like an AUC metric, could be something like a Sharpe ratio in a algorithmic trading strategy. This is basically just a number that if it goes up, we're happier with our model. So we basically want to be able to leverage what we've already observed to say, how do I think different configurations are going to perform if I were to try them? So a Gaussian process works by modeling all of those potential next configurations, the potential response from these next configurations with a Gaussian distribution. So there's some mean and there's some variance for the response we expect to see if we try different configurations. At the beginning, we have no information, so we can just maybe assume a uniform prior here and say, okay, I don't know what's going to happen next. But as we start to sample points, we can update the posterior of our Gaussian process to be able to say, now that I've already sampled this point here in the middle, I have an expectation that points near that are going to respond similarly. And all of a sudden, I have more confidence about sampling that region. And I also have maybe a better idea of what I'm expecting to see. So what this does is it warps this Gaussian process in such a way that now we have a different distribution for each one of these points nearby. And as we sample more and more points, we get a better idea of what that underlying system looks like. We get more certainty in certain regions, but this kind of allows us to characterize what we know, what we don't know, and what we expect to see. I'll pause here. It looks like there's a couple questions in the chat. How do you determine how well the surrogate model overlaps? Also, how steep is the trade-off between how well the model matches versus computational cost? So I'll answer that actually in two slides. How do Gaussian processes differ from? Okay, so Gaussian processes are different than using maybe a Bayesian neural network as your surrogate model. There's lots of different things you can use as a surrogate model. Once again, this is kind of the bread and butter approach to Bayesian optimization. Behind the scenes at SIGOPT, we use an ensemble of different methods. There's lots of great papers out there for using Bayesian neural networks as the surrogate model. You can use a random forest as the surrogate model. There's lots of ways to attack this. They differ quite a bit, though, in the actual mechanics of how they work. How you choose a data set size for testing model performance. Should it be a sample? So can I okay, so the data set size is kind of an orthogonal problem in this setting. So we assume that there is a model that needs to be tuned, and we want to be able to find the configuration that maximizes some configuration output. So you should build up your pipeline to make sure that it performs well out of sample. it doesn't misrepresent the results or anything like that. That's kind of the problem of building up a trustworthy AI pipeline. This assumes that you can trust the output of your system. So you give it a target and it will hit that target, but it assumes that that's actually the target you want to hit. So it's important to still do things like cross-validation, regularization, making sure that you can actually trust this metric that you're trying to optimize before you apply an optimizer, whether that's grid search or Bayesian optimization. So once again, for the graph here, we're assuming, let's say that we're tuning the learning rate, that's the x-axis here, and we're observing some objective output. So let's say this is an ensemble of different metrics related to the accuracy of a fraud detection pipeline. So maybe we care about accuracy, but we also want to penalize the system if it misses high value fraudulent transactions. So let's say that metric can go from -1 to 1. And as we tune the learning rate of our neural network, we can observe different potential kind of objective metric outputs. And so, and finally, the last question here, there would be the Gaussian process can extend to higher dimensional spaces. So I'm showing a one-dimensional one here because it's easier to plot. But yes, you can basically say for any combination of hyperparameters, we would observe a single scalar output, but you can extend the dimensionality of the hyperparameter space out. It gets a little bit tricky when you start to look at heterogeneous configuration spaces. So this is kind of a natural fit for continuous parameters like learning rate. But you can extend this to things like integer parameters, so maybe the number of hidden layers, or even categorical parameters like the activation function. But as you do that, the Gaussian process, basically the x-axis here would get more and more, that dimensionality can increase. There's a second way to think about Gaussian processes. I'm going to start to speed up because I see we're running shorter on time, but basically you can think about it from a functional perspective. So once again, we're trying to find a functional representation for what we expect to see when we sample individual configurations. At the beginning, any function in the universe could represent the output of this system because we haven't sampled it yet. So let's say we have a bag, and in that bag is every function in the universe. As we start to sample points, as we start to test these configurations, we observe an output, and all of a sudden, functions that don't pass through that output, if we sampled it with no noise, don't make sense anymore. So we can throw them out of our bag. What we're building up here is a distribution of functions that could represent the output response. And that the Gaussian process is effectively that distribution of different functional outputs. The most likely function is the mean of that Gaussian process. But as you can see, in these areas of uncertainty, other functions could represent the output. We just haven't sampled there to understand whether or not they do or not. So you can either think about the Gaussian process as an infinite number of expected Gaussian responses in the hyperparameter space, or an infinite number of functional responses in that response surface space. But either way, it provides this kind of very flexible way to model the underlying method or the underlying system that we're trying to optimize. We need to make sure that the Gaussian process fits the underlying data that we have. This was a question higher up in the chat. Basically, since we're going to be using the surrogate model to do optimization, we actually need to make sure that we can trust it. There's various ways to do but like any regression method, it's possible to overfit the data or underfit the data. These are 3 identical data sets, 3 different Gaussian processes. The one in the middle is the most likely given the data that we've observed so far. So we can explicitly calculate the likelihood of observing this Gaussian process. You can do that via marginal likelihood, via leave one out cross-validation. You can also explicitly model the various parameters of the Gaussian process as distributions themselves. The idea here is we want to learn how these points influence each other to decide what's the best possible way to model how they'll influence unknown configurations that we haven't tried yet. Couple quick questions here in the chat. So using Gaussian process for the hyperparameters and like this. Yeah, so Sepoli 2, you're not way off. Once again, lots of great books on this that dive quite a bit deeper. Highly recommend Gaussian processes for machine learning, which I've actually borrowed these figures from. Felicia, great next question. How do we actually use this as a sampling strategy for the parameter space? So once again, this is sequential model-based optimization. So the sequential component is we're learning from the history and leveraging that to decide what to do next. The model-based component of this is that we're using the history to build up a surrogate model, and we're going to leverage that surrogate model to actually come up with a sampling strategy for the actual parameter space itself. And so once again, there's lots of different surrogate models. You could use a Bayesian neural network, you could use a Gaussian process, you could use a student T process, you could do whatever it may be. We're using a Gaussian process here, but we're only using this as a stepping stone to get to some optimal sampling strategy. And so we apply an acquisition function to this surrogate model to decide what's the most intelligent thing for us to sample next. A very popular one is expected improvement. So intuitively how that works is we're trying to find the point that in expectation will beat the best thing we've seen so far by the most. So we're playing king of the hill. We have a single point here sampled in the middle. We want to find the point that in expectation will beat that point by as much as possible. Other popular acquisition functions are things like probability of improvement. So if I were to try a new configuration, what's the probability it beats the best thing I've seen so far? That differs from expected improvement because it doesn't care about the magnitude. You could also use like a knowledge gradient based approach, which is trying to learn about the eventual location of the optima. But once again, Bayesian optimization does not always mean Gaussian process-based optimization, and it doesn't always mean expected improvements on Gaussian processes. That just is probably the most popular approach. But there are many different approaches, some of them that work much better in different contexts, which once again is why an ensemble of Bayesian optimization techniques can usually outperform a single technique. But back to expected improvement here. So we can explicitly calculate how much we expect to improve if we were to sample these unknown configurations. So here there's kind of two equal areas. We're going to pick one. The sequential component of this allows us to update that surrogate model. So basically, now that we have this information about how that point performed, we know that it actually did very poorly. We're trying to do maximization here. It no longer makes sense right now for us to go back and sample near there because there's no longer any expected improvement to be had. So we then sample this next point sequentially. That updates our the posterior of our Gaussian process. We have this new surrogate model. This then influences where we think we have the best chance at expected improvement. Once again, intuitively, it's doing this trade-off between exploration and exploitation. So right now, this is a very exploratory point. We don't have a lot of information in this region over to the left. So we sample there to update, and now we have better information. Now we want to exploit this localized information here in the middle and sample that, going back to exploration here and back and forth. And basically, this acquisition function of expected improvement makes this trade-off automatically in the same way that a probability of improvement or knowledge gradient one would as well. How to work with ensembles? Do you pick the best in each area? Yeah, so an ensemble-based approach to this would be, let's say we, in some situations, we may be able to pattern match along the lines of being able to see, okay, when I'm observing this type of response, or this type of response from this underlying system that I'm optimizing, maybe probability of improvement works better than expected improvement, or if I have some total budget that I'm optimizing over, certain methods might work better in different with different amounts of data. Different methods scale differently. Different combinations of parameters. So once again, if you have continuous integer and categorical parameters, require slightly different approaches. So the ensemble-based method answering this question here in the chat allows us to kind of attack a wider breadth of problems and not get stuck in some of the kind of pathological downsides that specific approaches have. For example, expected improvement with Gaussian processes using Matern kernels tends to be very greedy in wanting to sample the edges of your configuration space. And there's different things that you can do by building an ensemble of strategies to make sure that you don't get stuck in kind of these local optima. Would your ensemble strategy stop iterating over a hyperparameter if that expected improvement drops below an already discovered one? Yeah, so once again, the nice thing about something like expected improvement is it won't over-resolve a local optima. The idea is once you already know what the result is going to be, there's no more utility or expected improvement in kind of continuing to sample that. You get more information by going out and exploring. And this is a global optimization strategy. Is there any built-in integration with this existing popular libraries? So yeah, SIGOPT has integrations with every popular library at sigopt.com/gallery or sigopt.com/docs. There are some open source methods that are trying to build integrations for different libraries as well. We did a few of that with the metric optimization engine, which we wrote at Yelp. Practical experience was when using the acquisition function to select points, is the exploration more important than the exploitation? Yeah, so this is extremely problem dependent, selecting the acquisition function, and you need to be able to see a large variety of problems in order to make that trade-off. The nice thing is these methods like expected improvements are analytically defined, and there's not really a knob for you to turn to say explore more or exploit more. That happens naturally, and it's built in such a way that it's kind of next step optimal. Is there any available source code to look at the implementation? Yeah, once again, lots of open source here. I would recommend checking out the metric optimization engine and BayesOpt and Spearmint. Those are great implementations of this. So I noticed that we only have about a minute left, so I'm going to run through one of these deep learning examples. There's a couple more that I'm not going to go over here. They're all available online. If you go to sigopt.com/research, we link to all of them. sigopt.com/examples has all of the code as well if you want to run them yourself, and kind of detailed instructions on how to get them up and running on AWS. So I'll post all those links that I just rattled off in the chat as soon as I'm done with the talk. Okay, so this was an example we did with AWS. It was on their AI blog in May. The idea was we're going to take kind of a simple convolutional neural network and apply it to a natural language processing task of classifying movie reviews. And then we were going to see how different hyperparameter tuning strategies performed in kind of optimizing the accuracy of this method. So once again, we kind of took an off-the-shelf method, off-the-shelf data set. We're just trying to tune for accuracy, and all we were doing was this black box optimization of changing the hyperparameter configurations and kind of architecture of that underlying neural network. Once again, lots of tunable parameters with neural networks, all the way from the stochastic gradient descent optimizers, which can affect how the actual weights are learned and whether or not it's converging. Once again, that's we're tuning this kind of meta problem, not replacing the stochastic gradient descent optimizer. There's various ways that you can represent the data itself. So how you tokenize the text, There's various parameters around the convolutional layers, dropout layers, etc. The standard ways to tune this, like if you go to a lot of the different open source libraries like scikit-learn and things like that, they have things like grid search and random search implemented for you, and they advocate for that. But we wanted to see what the difference was between that and something like Bayesian optimization. In this specific case, we were able to get a very significant speed up by leveraging NVIDIA GPUs to do the actual training and SIGOPT to do the optimization of the hyperparameters. The idea here is this is a multiplicative speed up. So every single time you make the model better or smarter or faster, by retuning it, you get this extra boost on top of it. So it's not like this adversarial thing where we're trying to do something completely separate. It's just taking the best of what you have and then making it a little bit better. And as you make it better, it's just kind of tuning it up. So this kind of goes without saying, CPUs are much slower than GPUs when you're doing training of these neural networks. We got about a 50x speed up by switching over to an NVIDIA GPU. We got about a 10x speed up by not doing random search, but by using Bayesian optimization to tune this underlying method. The way to look at these tables here is that in two different contexts, one where we were just tuning kind of stochastic gradient descent parameters, and one where we were also tuning architecture parameters, the Bayesian optimization methods were able to get to better results than random search, but also do so in 10 times fewer evaluations of the underlying system. The grid search approach, once again, in small numbers of parameters might be okay, but it scales exponentially, and so it quickly becomes intractable. Also, usually to make it tractable at all, the coarseness of the grid needs to be such that you actually don't get great results. In this case, I think it was just checking kind of the vertices of the hypercube of kind of potential configurations, as well as a few points in the middle. So when speed and accuracy matter, using intelligent search methods can make a pretty big difference. This kind of extends out no matter how many observations or how many underlying evaluations you do. And more information in our ICML paper, which I'll link to in the chat, about how you can kind of look at different optimization strategies extremely robustly to be able to see which one will perform well in general for these types of problems. Lots of other examples I'll link to here. I'm already over time though, so I'm not going to dive into a bunch of different details. All this code is available online. I'll send out all those links. Thank you all so much for spending some of your weekend with me. Really enjoyed this. Really great questions in the chat. Thank you all so much.